Hello everyone, in this video we're going to be talking about free radical halogenation reactions of alkanes. Alkanes undergo only one type of reaction, that's going to be conversion of alkanes into alkyl halides that you guys are going to be learning in organic chemistry. Alkanes indeed undergo reactions like combustion reactions and also higher hydrocarbons can undergo a reaction to make smaller hydrocarbons, but those other two types of reactions you're not going to be learning them. However, the main type of reaction that you guys are going to be learning in sophomore organic chemistry is the conversion of alkanes into alkyl halides. So if I write a generic reaction, suppose I have a hydrocarbon, and I can take in a simple hydrocarbon as in a CH4, and this CH4 is going to be added into the halogen. So I'm going to go and write down X2 for right now. And this has to be catalyzed by the light. So you can have either the light or you can even have the heat. For the light, you may see this symbol being written, so be familiar for both of those terminologies there. And then at the end of the day, it's going to be replacing one of the hydrogens by the halogen there. So I'm going to be ending up getting CH3X there, and I'm going to have HX as my side product there. So that's going to be the conversion of alkane into an alkyl halide, and you guys done a lot of reactions on alkyl halides, whether it's an SN1, SN2, or E1 and E2. So that kind of opens up the whole organic chemistry into doing multiple reactions. But when you're starting from alkanes, you have to do this only reaction that you're going to be learning today. This reaction does takes place through the formation of a radical. And I just want to kind of remind you guys how the stability of the radicals works. So recall that your tertiary radical is going to be more stable than the secondary radical, and your secondary radical is going to be more stable than your primary radical. And remember, if you have a allylic and benzylic radical, they are going to be even more stable. So that goes back to the stability of your radicals. If I want to go ahead and write down a benzene there, the benzylic radical is going to be even more stable because of all the resonance that can take place. And same story goes with the allylic. The allylic radical is also going to be more stable than your tertiary radical because of the resonance. But when I'm comparing the benzylic versus allylic, the benzylic is going to be more stable because it has more resonance structures than the allylic. Obviously, you're not going to be only limited to those primaries, secondaries, and tertiaries. You may see these benzylic and allylic radicals as well. So make sure you know what the stability order for the radical is. So let's talk about this X2. I just mentioned that we're going to be using a halogen there to make these alkyl halides, but okay, what's going to be the best halogen? So these X2 could be either fluorine, could be a chlorine, it could be a Br2, and could be an I2. So out of those four, we focus only the middle two ones, and the reason why this F2 reactions are very exothermic, and since they are very exothermic, they could be explosive sometimes. So you're not going to be using an F2 at all. So we got to write down cross there. We're not going to be using that. As far as your I2 go, these reactions are too slow. So since they are too slow, that takes forever, so we're not going to be focusing on that either. Now, the focus comes down to your Cl2 and the Br2, and even between the Cl2 and the Br2, there is a big difference when we're using those as our halogens. So Cl2 compared to the Br2 is more reactive. And this being more reactive, it's actually going to be less selective. Now, you may wonder what this term really means, less selective. So hang on to that. We'll talk about what the selectivity means. But just know for right now, chlorine is going to be more reactive and it's going to be less selective as a result of this being more reactive. But on the other hand, when we look at the bromine, bromine is actually the opposite. I'm going to make a space there, write that on the right side there. The bromine compared to the chlorine is going to be less reactive. And since it's less reactive, it's going to be more selective. So it has an advantage over the chlorine. So we'll talk about that, but just for right now, know which one is more selective and more and less selective, and also in terms of the reactivity. So we're focusing on only chlorine and the bromine, and even later on, you guys are going to be learning that bromination is actually going to be your best friend out of all those, and we kind of ignored the fluorine and the iodine already because one being too fast, that's going to be explosive, and the other one being too slow and takes forever. So that's going to be your halogen. Now let's talk about which hydrogen you're going to be removing. Like we talked about as in a generic reaction that we have in a CH4, but you're not really going to have just in a CH4. You can have any hydrocarbon where you're going to have in a primaries, secondaries, and tertiary carbons. And the question is which one you really want to remove. And it comes down to the selectivity of the hydrogens. And now, usually, you're going to have your tertiaries, carbons that bearing the hydrogens are going to be more selective than your secondaries, and those are going to be more selective than the primaries. And I can actually go ahead and put the allylic and benzylic in front of those because they are going to be even more selective in terms of your selectivity order. And that actually is true for both chlorine and the bromine. However, the selectivity, the capacity of selectivity is indeed different for the chlorine and the bromine. So chlorine, even though it's going to be in chlorination, you're going to have tertiary hydrogens to be more selective, more likely to be abstracted than the secondaries, but how much more, that depends on whether you're doing the chlorination and the bromination. So like we said, the chlorine bromination is actually very, very selective, and we'll talk about those in a little bit. But an overall order is still stays true, that tertiaries is still going to be more reactive than the secondaries and then the primaries. So be able to identify your hydrogens. So in this particular case, let me go ahead and um, kind of write down all your primaries carbons. So this is primaries carbons right there. So all these guys are going to be making primary radical when you remove your hydrogen from those carbons. Okay, so then what else we have? Let's look at maybe another one there. We have this carbon and this carbon right there. Those are bearing two hydrogens. So when you remove one of those hydrogen and makes a radical, that's going to be making a secondary radical. So make sure you know to be able to identify your radicals there. So and then what else we got? We have another one right there. You got this one right there that's got one hydrogen on here. So once you remove that hydrogen, it's going to be ending up making a tertiary radical. So you're going to call that tertiary hydrogen. So that's there. And then you're going to have an quaternary. Your quaternary carbon is kind of useless because your quaternary carbon does not have any hydrogen on it. All right, so no hydrogen atom on it. So it doesn't really matter. You don't really want to focus on that much on that one too much. You're only going to be focusing on either primaries, secondaries, and tertiaries. And just make sure you know your benzylic and your allylics as well. So just to kind of on a side note there, if I go ahead and draw a, let's say, 2-pentene here, then your allylic positions are going to be this one right there and another one right there. So you could get multiple products in those cases. So those are going to be your allylic positions, and you can also have obviously your benzylic positions, and I expect you to know that, but just as a refresher, your benzylic position is going to be right there. So that's going to be your benzylic position there. Okay, so that's all we really need to know so far as being able to figure out the type of hydrogens and the selectivity of the hydrogens. Now, let's talk about how do we know that bromine is going to be more selective than the chlorine, and so on, and how that's going to make a difference in the product. All right, so one thing you do want to know that you could very well have in a monochlorination versus polyhalogenation, whether it's chlorination or bromination, doesn't really matter. So in terms of taking this as an example, so suppose I got an CH4 reacting with a Cl2, and if you have the Cl2 in excess, you would make this CH3Cl in the first step, and obviously your side product is going to be HCl. I'm not going to write that down because that's your inorganic product. You focus only on organic products when you take organic chemistry. And then if you have an excess Cl2, it's going to keep doing it. It's going to keep reacting with it. And the second time it becomes even more reactive. So it's going to end up making CH2Cl2 now. And then it will keep doing it until you will replace all of those hydrogens. So at the end of the day, you're going to be making carbon tetrachloride there. And the question is, how do we really control it? One way to control it, you can use a very small amount of chlorine, and you're going to use an excess CH4. If you use an excess CH4, then you will end up getting only one substitution there, or yeah, one substitution there where you're going to be only making the CH3Cl in that case. But if you use an excess of Cl2, there's a good chance this reaction goes all the way to make the CCl4. So that's one type of question, like, okay, what's going to be monohalogenation versus polyhalogenation? But a lot of time we're going to be assuming, we're going to be focusing that we only doing the monohalogenation, because doing halogenation is kind of useless unless you're trying to make carbon tetrachloride. Then it's a different story. But you're going to be focusing only on monochlorination or monohalogenation in this chapter. Obviously, someone may wonder, like, if you get the mixture of these products right there, let's call this A, B, C, and D, how would you really kind of separate those? You can actually separate those by using fractional distillation, because all these guys, they're going to have a different boiling point. So you can use fractional distillation to kind of remove those if you indeed make all four of those in the reaction mixture. But obviously, whenever you make multiple products, it's kind of a bad reaction to run. You always want to try to minimize one type of to make one product. Let's talk about the monohalogenation now. So suppose I'm running this reaction with propane with Cl2. Now I know I have two different types of hydrogens there. I got a primary right there. So I got 6 of those if I want to count those. So that's going to be 3 here and 3 there. So that's going to be a total of 6 hydrogens that are going to be primary. And then you also have 2 hydrogens on this second carbon, so those are going to be your secondaries. So we did say earlier that, okay, usually your secondaries are going to be more selective to more likely to be abstracted than the primaries, but chlorine doesn't really do a good job in terms of abstraction of protons. It does a decent job, but not a good enough job to kind of qualify as your best friend in terms of halogenation. So will end up getting products like an SCl there, and the other product you're going to end up getting is going to be the chlorine here. So those are going to be your 2 products there. And as far as their percentage go, I'm going to be getting about 60% of this secondary isopropyl chloride, technically, and then this propyl chloride is going to be about 40%. So even though you had 6 primaries, hydrogens, you still only get 40% of that, but you had only 2 secondary hydrogens and you get 60%. So you can clearly see that you do have a selectivity toward the secondary protons, and the chlorine was more leaned toward removing the secondary protons than the primaries, but even like 60-40% is not a really good reaction to run. But when we compare this with the bromination, it actually makes a huge difference because bromine is even more selective. So when I'm doing bromination of the same compound, I will get 2 products. But in terms of their relative percentages. This secondary bromide here, which is going to be isopropyl bromide, is almost going to be 98%, and this is going to be about less than 2%. So that's a very big difference in terms of the selectivity. So that's why we said, okay, bromination is going to be your best friend because you're going to have this being very selective compared to the chlorination. So from now on, you guys going to be doing the bromination for the most part whenever you're doing these synthesis reactions, but that doesn't mean that you will not see any questions on chlorination, because sometimes you may be asked how many different monochlorination products you can get in a given reaction. Like in this next one here, I have this example here. So how many different monochlorination products you can get. So let's talk about that. So I'm going to go ahead and copy this down multiple times because I got multiple, maybe another one here. Because if you think about it, I got how many different types of protons I got here, or hydrogens rather. I got this and this is going to be the same. I got this is the second type, this is the third type, this is the fourth type. So they will make different constitutional isomers there. So I could have a chlorine here. So either I have chlorine on that one or the other one that we have designated as first, it doesn't really matter. I could have a chlorination here. I could have a chlorination here. And I could also have a chlorination here. So you could actually get 4 different products in this particular case. But when it comes down to bromination, bromination is very selective, and it's even more selective for the tertiary carbon. So the only tertiary carbon you have is the second one there. So at the end of the day, your product is going to be this guy right there. You're going to have bromine there. And this product is always going to be more than 99%. So you don't really have to write the other ones. But as far as the other goes, the 4 products you get, they're going to have a relatively good amount of percentages. It's not important to know what the exact percentage is going to be, but it's important to know that you could see all those different products when it comes down to the chlorination. But when it comes down to the bromination, it's very selective and it's going to be focusing on only some of those, only the tertiaries and the benzylic and the allylic hydrogens in that case. Now, why that really happens, I'm going to quickly talk about it. I'm not going to spend too much time on it. So we talked about between the bromination and the chlorination, the reaction between the chlorination and the bromination. The chlorination is actually an exothermic reaction, and we're talking about the rate determining step. So these energy profile diagrams that I have drawn. So this one is for the Cl2 addition, this one is for the Br2 addition, and obviously these are only for the rate determining step, which is going to be the first propagation step, and we'll talk about that in a little bit. And you can clearly see that, okay, I'm starting from the products, from the reactions there, and I'm making these primaries and secondaries and tertiary radicals in case of chlorination. When it comes down to these transition states, the energy difference is not big enough in those cases. So that's why you could see both the primaries, secondaries, and the tertiaries as well. However, the activation energy for the tertiaries is indeed going to be the lowest. So that's why it is more likely to take place. But if I want to compare the activation energy to make the tertiary radical compared to the activation energy to make the primary radical, obviously um, the energy difference is not big enough. So that's the take-home message in case of chlorination. So when I'm looking at your bromination there, so the bromination is on the right side, it's actually going to be an endothermic process, that particular step. And in case of chlorination, you can clearly see that it's an exothermic reaction there. And there is a big difference in terms of your activation energy. So this is going to be the activation energy for your to make the tertiary radical. But when I'm looking at the activation energy for the primary radical, it's a very big difference there. So that's why these brominations are actually going to be very selective compared to the chlorinations. And in terms of Haemons postulates, if I want to kind of, just kind of go back and re-look at it, so this chlorination, when I'm looking at what's really happening in the transition state. This transition state is actually closer to the reactant, all right? And in case of bromination, your transition state is going to be closer to the intermediate, or you can say the product, which is obviously going to be some sort of radical there. So since in case of chlorination, it's closer to the reactants. So if I go ahead and just randomly pick this propane here, so I'm about to break this bond, and I'm about to get the chlorine radical to get the hydrogen there. So there, the bond breaking is not as prominent in this case because this transition state is closer to the reactants. But when I'm looking at my bromination, in case of bromination is actually going to be a little bit different. So I'm just going to erase that. In case of bromination, you have the transition state closer to the intermediate, which is a radical, which means the transition state has a very large character of the radical formed already. So you're going to have a hydrogen kind of almost broken in that particular case. So you're going to have a good radical character in case of the bromination, but you're not going to have a good radical character in case of chlorination. So you can see the difference in the bonds there. You have a shorter bond between the carbon and hydrogen. You got a very long bond between the carbon and hydrogen in case of bromine, and that kind of tells you that it's going to be you almost have the bond broken in that particular case. So that's your Haemons postulate. So sometimes they ask you, okay, well, if the transition state is closer to the reactants, how your transition state is going to look like, and if it's closer to the products, how it's going to look like. So you can predict based on the original structure of the reactants and your intermediates there. And obviously that's all kind of goes back to these rate determining step being exothermic and endothermic, and a big difference in the activation energies in case of chlorination and the bromination. Okay, so what happens if you have a double bond? So suppose I'm dealing with a reactant that looks like this, and I'm doing a Br2 here with light. Now, if you recall, this Br2 can also be added to your double bonded carbon. So that's your addition reaction there. I'm not going to worry about the stereochemistry there, but that could also happen along with if you're trying to do the radical halogenation, it may not happen. So there is going to be a competition there. So you may get a little bit of a radical there, uh, and you may get a little bit of the bromination there at the allylic position, but there is obviously a competition, and this may end up being the major product in there, and you want to somehow avoid this competition there. And to avoid this competition, you can always minimize the bromine concentration. And one of the ways to minimize the bromine concentration is by using something called an NBS. So instead of using the bromine, you use another chemical that has the bromine in there, and that's going to be called the NBS, and you still use it in the presence of light. And this allows you to minimize the concentration of the bromine, and as soon as the bromine is produced, it's going to be reacted at your allylic position. So that way you can only make the allylic alkyl halide, allylic halide there instead of doing the addition reaction. So remember, whenever you have a double bond, don't use Br2 because you may run into the addition reactions in that case. And to avoid that, you want to go ahead and just do the NBS reaction. So how does the NBS really look like? You may not have to know that how the NBS looks like, but it's usually a good idea to kind of know um, the structure just in case if somewhere it pops up. So it's a cyclopentane ring, and it's got the nitrogen there. It's a 5-membered ring, and you got an Br there. So this nitrogen bromine bond is also weak, and you can do a homolytic break of this bond where you can create the radical there. So that's a way of using the NBS, and you can use that as a source of bromine. So let's talk about your mechanism now. So when we talk about mechanism, there are actually going to be three steps. The first step is called an initiation step, where it's going to start out with the formation of two radicals from a molecule or from a compound. So if I use, suppose, a Br2, and in the Br2, I'm going to be using that in the presence of light or heat, and we're going to be getting these homolytic breaking of the bond, where this bond breaks and the one electron goes onto the one bromine and the other electron goes onto the other bromine. So that's why you can see these arrows being drawn with the half head, and that's it's important to make sure you draw like those whenever you're doing these radical mechanisms. You draw a full arrow, two-headed arrow, whenever you have these simple reactions, whenever you're making ions, but when you're doing radical reactions, you have to draw this half arrow there. So that's going to be two Br radicals being made. So that's going to be your creation of two radicals from a molecule. So be able to identify your steps are there. So this is going to be your initiation step. So then I can go ahead and do this one as well. So if you're using an NBS, suppose it's going to be very similar. I'm going to be doing a homolytic cleavage there, where one electron goes onto the nitrogen and the other electron goes onto this bromine there, and I'm going to be getting two radicals there. So I'm going to copy this down, erase a part of it. So I'm going to have a radical. So I'm just going to draw a radical there. So remember, this nitrogen also have two other lone pair, one other lone pair there. So if I want to go ahead and draw that, but there is a radical now on it. And then these bromines, remember the bromine itself has three lone pairs of electrons, and obviously it's going to have the radical on it. So you may see these bromines kind of being drawn with three lone pairs and one radical, or you may see these bromines being just drawn as a Br with a radical. So once you have created these radicals, your propagation step is going to be you use a radical and a compound, and you make another radical and another compound. So make sure you're able to identify your uh, propagation steps. I'm going to just take an example of maybe this propane here. So I'm going to go ahead and draw the secondary hydrogen there. And then obviously the Br radical is there. So this carbon and hydrogen bond is going to break. So this is going to break homolytically. And then obviously this bromine is going to react with the hydrogen there. So this is how you're going to draw the arrow there. And then you're going to make a radical, which is going to be the secondary radical now, and you're going to be making the compound as an HBr. So that's going to be your propagation step. You started with a compound and a radical, and you made a different compound and a different radical. So that's an important thing to be able to identify. Okay, so then the other type of propagation step you could possibly have. So suppose I'm having this radical here, and then I'm reacting that with the molecular bromine. Because once your initiation step has been taken place, and once you have created the radical, it doesn't matter which radical you use to kind of break up this bromine after that. So I could break this bromine homolytically again, and then this right there, and obviously this is going to combine with that. So at the end of the day, you're going to be getting a bromine there and your Br radical there. So that's another propagation step. So as long as you're using a compound and a radical, and you're making another compound and another radical, that's going to be the example of propagation step in that case. So make sure you're able to identify your propagation steps in there. Then the last thing you're going to have is your termination step. The termination step, you're going to have two radicals combining to make a compound. And you can have different types of termination steps. So you can have, two bromine radicals kind of coming together to make a compound. or I could have, if I go back to the original reaction that we were doing earlier. So let me go ahead and copy this. Um, oops, copy this down. If I have this radical, and suppose I get a bromine radical there, so they could combine together. And when they combine together, they're going to be making a molecule now. So that's another termination step. The other termination step you could possibly have here is I could literally have two of these guys and another one of those, and they could combine with one another. Now, it may not happen, but it's a possibility that it would. If it does happen, then you're going to get this side product here, which is going to be uh, minor in there, but it's a possible termination step as well. To be able to identify your termination step. Now, at the end of the day, I do want to mention something about the stereochemistry of these compounds. Like, suppose I'm having this maybe butane here, and I'm running a bromination here. And you remember the NBS that you have learned earlier that you're using this with whenever you have the double bonds present. You don't necessarily have to use the NBS only when the double bonds are present. You can use it whenever you're using these alkanes as well. But if you have a double bond somewhere close by, then you want to make sure you don't use Br2 by itself, because that's going to also do an addition reaction. However, that does not apply to the aromatics, because aromatics does not do any addition reaction that you're going to learn in second semester. Now, I know I'm going to be making a more selective, I'm going to be removing a more selective proton here or hydrogen here, which is going to be the secondary. And in terms of the mechanism, I'm not going to draw the full mechanism, but remember, this is going to be making this radical here, which is going to be the secondary radical. And remember, this secondary radical is going to be a planar structure. It's going to have an sp2 hybridization because this radical is going to be in unhybridized p orbital. So since this is going to have an sp2, when you bring your bromine radical to make the compound, it could do a top or bottom attack. So you have actually the possibility of making an enantiomer in there, because you have almost a 50-50 shot of having these bromines either out of the page or going back into the page. So in that case, you can get racemic mixtures. Now, you only get racemic mixtures, or you only going to get enantiomers if you only have one chiral center, obviously. If you already have a chiral center in the molecule, then remember, you're going to be making a pair of diastereomers in that case. But that's the bottom line. That's going to be your stereochemistry in that particular case. Now, anytime you're doing these, suppose these allylic ones, the allylic ones are going to be a little bit different in the sense that it could have a resonance structure. Suppose I have a double bond right there. So then if I'm doing the Br2 on that with NBS, obviously, then I could actually make two different products there. And one of the products is going to be where the bromine is in and out of the page right there. Or the other products you can have when you have this resonance where the double bond is going to move onto the new location there. So it's going to move down here, and you're going to have a bromine here. So this one is not going to be, it's not going to be your chiral center, so you don't have to worry about drawing this bromine in and out of the page. Now, how does that really happen? Why do you get this third compound there? That's because when you create this radical, I'm not going to draw the full mechanism, but remember, you're going to be removing the hydrogen from this carbon here. And when you remove that hydrogen from that carbon, you're going to create this radical there. And this radical can have the resonance structure now. So where make sure you know how to draw the resonance structures there, so you can have movement of these electrons there, and you're going to have the radical down here as well. So you're going to have a lone pair, you're going to have a radical there. So those two possible resonance structures can make these different products there. So if I use this, obviously this first one is going to be making these two products right there. And obviously if I'm using this second radical there, I'm going to be making this product there. So be able to identify your different possibilities of the products in that particular case. So this is pretty much all you really need to know about the radical reactions. Obviously, knowing what's more selective, what's more reactive, and knowing the mechanism, different steps in there are going to be the most important things. And the take-home message is, if you're starting out with alkanes, the very first reaction you're going to be running on alkanes is this free radical halogenation. That's the only reaction you guys are going to be learning in sophomore organic chemistry. All right, if you have any questions, feel free to leave any comments in the section below.